All right, howdy. All right, so a little bit of business first. So, yeah, it's all right. Yeah, go on and sit down. Tonight, a Canvas quiz based on tonight's lecture will open up at about 7:30. There'll be an announcement that comes with whenever it's available, and it will close at 1 a.m. So during the talk, all you need to do is pay attention, be respectful to your peers' ability to pay attention, and then if you want to take notes, you're welcome to. For those of you who have issues or something with the Canvas quiz, there'll be an alternative assignment that'll be available to everybody, and it'll be open probably for 7 days. We'll send more information about that once we kind of get through all this, okay? All right, so now I'd like to introduce our speaker. Tonight's speaker is Sherry J. Yennello. You can see her picture up there. She is a university distinguished professor and Regents Professor of Chemistry and Director of the Cyclotron Institute, and holds the Bright Chair in Nuclear Science at Texas A&M University. She received her PhD in nuclear chemistry from the national football champion, Indiana University. Spent 2 years as a postdoctoral fellow at Michigan State University before arriving here at Texas A&M in those long gone days of 1993. Since arriving, she has accumulated many accolades and awards. Some highlights here. She is a fellow of the American Chemical Society, American Physical Society, and the American Association for the Advancement of Science, the AAAS. Her research has been recognized with ACS's highest honor in her field, the ACS Glenn T. Seaborg Award in Nuclear Chemistry. You might recognize that name from the periodic table, as well as she's won the ACS Garvin-Olin Medal. Next month, Dr. Yennello is going to be recognized with her most recent award, the Texas A&M Association of Former Students Distinguished Achievement Award for Research. She's already received the Distinguished Achievement Award for Administration and Teaching. She is one of only 5 of our faculty members who have earned 3 AFS awards. So she is an internationally renowned nuclear chemist, an expert in heavy ion reactions. She also oversees our leading US program in developing alpha-emitting radioactive isotopes that are transforming nuclear medicine as an effective treatment for inoperable tumors. So that's what she's going to be talking about a little bit today. As a proven force for good, the Cyclotron Institute is the world leader and the global gold standard in radiation effects testing that benefits national defense and commercial sectors. So they just had a facility expansion that was recently approved by our Board of Regents. Each year, the Institute delivers 10,000 beam hours for commercial, government, and educational uses, and is one of 2 US suppliers of AT211 for targeted cancer therapy, in addition to radiopharmaceutical purposes through our Department of Energy National Isotope Development Center. So this is something that you're going to hear in her presentation. Let's give a warm welcome to our speaker tonight. Thank you.
Who here knows somebody who's been impacted by cancer? Look around, you're not alone. You're clearly not alone. Cancer takes far too many lives here in the United States and around the world. It's in fact the #2 cause of cancer cause of death in the US. And some of those people who we know that have been impacted by cancer have unfortunately passed away. Others were fortunate enough to get really good treatment and survive, but often at the expense of a lot of side effects and some loss of quality of life. And you may know that in your friends and family that have had cancer as well. So what would you say if I told you at a fairly nondescript building on campus, there's an instrument and there's a team of people that are working really hard to try to change that statistic, to try to make it so more people survive cancer and those that survive do so with less side effects? I'd call that a force for good, and what we do here in Aggie Land. So I'm going to tell you, so first I'd like to say howdy. Thank you for joining me this evening. I know this is a competing with some basketball games, but you'll be able to catch the second half. That's okay. And by then we should have the games well in hand, right? But I'm going to tell you a little bit about our program based at the Cyclotron Institute using a cyclotron that was built in 1960s, okay, long before you all were born. The cyclotron was built here to study the universe, okay? So let's back up and say, okay, so I actually was meeting with some former students today, and I asked them, what enables life on Earth? And one person said, sunlight, which is a perfect answer, because the sun gives us light for photosynthesis, gives us heat so that we can survive here on Earth. And what is the sun? It is a great big ball of nuclear fusion. It's just a bunch of nuclear reactions that are absolutely necessary for life here on Earth. So it's important that we understand nuclear reactions to be able to understand one of these fundamental requirements for life on Earth. Where do the elements come from? You guys are all mainly in chemistry now, right? So you've got that whole periodic table, including astatine, AT, element number 85. Where did they come from? They come from the stars, okay? They come from stars, they come from supernova. When you go out at night and you look up at the stars, you should be saying, look, there are nuclear reactions that are filling up my periodic table, that are reaching the ends of the periodic table. That's all going on, and it's all nuclear chemistry. And so when the cyclotron was first put here in Texas A&M in the 1960s, it was done with a joint effort of the Atomic Energy Commission, which was the precursor of the Department of Energy, the state of Texas, and the Robert A. Welch Foundation. So these gentlemen got together and said, there's this little school out in California, I think it's called Berkeley. They have one. We should have a better one. So in fact, that's what we did. We looked at what they built, and we built a better one, and to do discovery science. 30 years or so after that, we realized that there was another way that we could use the infrastructure, both the physical infrastructure and the intellectual infrastructure that was at the Cyclotron Institute, to be a force for good. And that was because, well, is there ever too much of a good thing, right? We said the sun was essential for life here on Earth. But what about too much of it? I get sunburned all the time, so that's aside the point. But if the sun gets excited, then you could have solar flares. And if you have a solar flare, what it does is it puts lots of ionizing particles into the atmosphere, okay? Some of these particles get trapped around the Earth, and when we have satellites up there, they get impacted by these ionizing particles. So if your cell phone doesn't work because there's a solar flare, it's because something failed on a satellite. We need these satellites for our communications. We need them for basic exploration. Every NASA mission that goes up has electronics on it that are susceptible to this solar wind and the ionizing particle. When the Dragon crew capsule went up, taking manned space, all those parts were tested here because we realized 30 years after the cyclotron was built for discovery science that we could use our heavy ion beams to test the electronics before they went up in the satellites to make sure that they would withstand the radiation that they were going to experience in this very harsh radiation environment. And we do that today. Ed already told you we are the #1 place in the world where people come to test electronics so that we know our satellites are safe, as are everything we put in space. On top of that, now we worry a little bit about autonomous vehicles, right? Whether you've been in a Waymo, or maybe you just put your car on cruise control and let it tell you how you're supposed to parallel park. All of that depends upon the electronics in your car working. And if they don't work, we don't want to contemplate what will happen if the Waymo goes off kilter, right? But as electronics get smaller, the incidence that there's an issue gets much greater. And so there's a lot of concern with autonomous vehicles. And so we're starting to test those electronics as well. So that was like where we moved from purely discovery science into saying we're going to be able to give back to society, to the American taxpayer in another way. And that was through this radiation effects testing. If I fast forward another 30 years, because we've been around a while, did I tell you the cyclotron was built in the 60s? Then you get to the idea that a new modality for treating cancer could be targeted alpha therapy, okay? And we're going to talk about that today, and hopefully you'll know what all those words mean at the end, okay? In order to talk about targeted alpha therapy, I wanted to introduce you to Klaus, okay? He's patient number, case number, something in the literature, but I think everybody deserves an actual identity. So I called him Klaus. So we'll call him Klaus tonight, okay? So this image here, all of the dark spots in this image are indications that a radionuclide has been absorbed and there is likely cancer there. Okay, there are some where you're excreting the isotope out of the body, but for most parts, everywhere you see a dark spot, Klaus has cancer. Okay? He's a real person. This is a real image. He was given very little time to live. They had tried every conventional avenue to try to save his life. And in Germany, they have a compassionate care policy that when his doctors told him and his family, get your affairs in order, there really is no possibility, they could try an experimental treatment. And I'm going to tell you about that today. And at the end, we'll revisit Klaus. Okay, so our story begins a very, very long time ago. Okay, does anybody know who this is? Marie Curie, okay? So she was very, very important in the beginning studies of radioactivity, okay? In fact, she is the only person to have not won one, but 2 Nobel Prizes in 2 different categories. She won the Nobel Prize in Chemistry and the Nobel Prize in Physics, okay? She was a pretty remarkable woman, okay? She, as the war started, she was in Poland, decided she had to get out of Poland, and so she took all of her sample and she actually locked it in a vault in Paris and had to put her research aside, all of the very important research she was doing, basic fundamental discovery research on radioactivity, okay? Had to set that aside for the war. She felt like she needed to do something for the war, but as a young woman, they weren't about to send her to the front. So she said, there's a better way. There's another way I can help, okay? X-ray machines were just starting to be used in hospitals. And what Marie Curie did was created this thing called a little Curie, which is an X-ray machine in a mobile vehicle, okay? And so they were able to take this to where there were injured soldiers and be able to X-ray soldiers and identify things like where the bullet was in the soldier so that they could remove it, okay? She then realized that one car could only do so much, and the war was having large impacts. So she recruited women from France mainly that wanted to learn how to operate this X-ray machine and learn about radioactivity. So she became a teacher, and she taught these other women how to be able to do what she could do. And then she went to like rich women in Paris and said, you know, we really need to help here. And she gathered up enough money for 20 of these vehicles to be put together. And all told, Marie Curie took her discovery science and had this application of it with 20 of these vehicles. She trained 150 women in nuclear science and radioactivity and X-rays. And estimates are there were well over 1 million soldiers who were able to get better battlefield care because there was an X-ray taken there where they were hurt. So she's pretty remarkable. And she taught us about imaging or radiation for diagnostic nuclear medicine. Okay? Now, probably who's had an X-ray, right? Everybody gone to the dentist, maybe you fell playing soccer, thought you broke a bone. We've all had X-rays, right? We owe this back to Marie and her colleagues many years ago. The other thing that radiation can do for us is to treat cancer. And this is maybe the first thing in a journal about actually using radiation, the radium rays, for the treatment of cancer. Again, well over 100 years ago. So what we do today is based on the shoulders of these two remarkable women, Margaret and Marie, and many of their colleagues. Okay, so we could talk about X-rays. You guys, many of you said you'd had an X-ray. So how do you get this image? An X-ray is just electromagnetic radiation. And if you shine it through a hand, it penetrates through the soft tissue, gets absorbed by the bone so that you can get this image. And you can see not only the bones, but you can see the ring and the bracelet because heavy elements tend to absorb these X-rays, okay? But when I showed you the picture of Klaus, that wasn't an X-ray. That was not external radiation going through a body imaging in a transmission mode. It was more like this PET scan, okay? So you can see here the hot spots on this mouse. This is actually a terbium mouse. But so if you want to study structure, where the bones are the bones broken, is there a bullet in the soldier, where is the bullet? You can do that with a static image from an X-ray, shining the X-ray through the body. If you want to watch a biological pathway taking place in a body, you need to be able to follow that biological pathway, and you need to be able to have the radiation coming from where things are happening in the body, okay? We do that in two ways. One is called SPECT and the other is called PET, okay? But basically what we're doing is giving a patient something in their body that will follow a biological pathway and emit gamma rays. Okay, gamma rays are just electromagnetic radiation, just like those X-rays. They're a little bit higher energy in general. They come from the nucleus rather than the atomic levels. Electromagnetic radiation. They will emanate from the body, again, going through the soft tissue, relatively unimpacted, and then you can image it with a camera. Okay? So we could do an analogy here, okay? So let's pretend at the end of fish camp, we took all the new students and we let them out on the golf course for a little scavenger hunt, and we gave them each a flashlight, right? And as they went around campus, there were actually a number of little gatherings or parties, right? It might be that there's, some people from the football team, and then there's some people, from the science club, and there's a fraternity that's having a gathering here and there. People would tend to gather at those, right? And of course, since there's a little gathering and a party, there's food. So when you get there, you have something in common. You spend some time and chat. What would happen? You all have a flashlight. If one were to take a detector over the top of campus, a drone, and look, we would start to see those lights accumulate and cluster where there were centers of activity, right? So then we could be able to tell, looking at the flashlights from the overhead detector, there's a party there. There's a gathering of students there. And that's what we do with SPECT or PET, is we give the body a molecule that's going to go seek something in the body because of its chemical behavior, but it's going to carry with it a radionuclide that is going to emit this electromagnetic radiation, just like coming from your flashlight. And then you're going to see these hot spots, in this case, where they had injected a tumor into this mouse to see that the terbium goes to the spot of the tumor. Okay? So that's the diagnostic part, is being able to see that because we have this tracer molecule, okay? We can watch your brain work by giving you fluorodeoxyglucose, which brings a fluorine 18 attached to a glucose, and as you think, your brain uses glucose, and one can watch it. Psychologists do this. I don't do that, right? You can watch your heartbeat if your physician thinks there's a heart issue by watching these gamma rays coming out, following these biological pathways. Okay, so we have diagnostic nuclear medicine, and we have therapeutic nuclear medicine, and let's talk about if somebody has cancer. So when my father had skin cancer, fortunately he was not like Klaus. He had some skin cancer on his hand. They were able to go in and surgically remove it, right? It's small, it's isolated, it's readily accessible, and you can surgically remove it. That's great, right? That's a tool the medical community should use, okay? But if that's not the case, and the cancer is somewhere else, we might need some chemical warfare, right? So people have had chemotherapy, where better living through chemistry, you can deliver a lethal dose with some toxic chemical to the tumor, but it is impacting the rest of the body, right? So, it's a trade-off. But again, another valuable tool for the medical community to have. Or we can think back to Marie and Margaret and say, what about radiation? Okay? So later in life, when my father had prostate cancer, he had external radiation treatment, okay? So they put him in a machine, kind of like this, and they shoot gamma rays through the healthy tissue to get to the tumorous tissue, okay? You distribute the load on the healthy tissue by coming in at various different angles so that you try to cause more damage to the tumorous tissue than the surrounding healthy tissue, okay? Often very successful. But you have to go through the healthy tissue first before you get to the tumor. So what would happen if you could actually bring the radiation to the cancer site, not have to go through the healthy tissue? And the first real example of the power of alpha particles and internal radiotherapy. So down at MD Anderson, they used to implant gold seeds that were put in our reactor here, and then they could again radiate from the tumor. But I want to tell you a little bit about Xofigo. Okay, it's kind of a funny name, but okay. We all know that to have those strong bones so that while you're playing football, you don't break your bones. You got to have a lot of calcium, right? Everybody's told, drink your milk when you were young, okay? Calcium goes to the bones. If you remember Klaus's picture, he had tumors all in a lot of his bones. So what if I had something that was an analog to calcium that could bring radioactivity to the bone? So now, I think this is a laser pointer. Oh, maybe not. Okay. You see, again, you're familiar with the periodic table, and I give you a piece of it here. There's calcium, which goes right to our bones. We need it for our bones. And you go down a couple of rows, and you get to radium. Okay? So because radium has the same external electron configuration as calcium, it could behave much the same. And so someone thought, well, maybe radium will go to the bones like calcium. It should behave like that. It's a homolog. And so they gave some patients with cancer that had metastasized into the bone radium dichloride with radium-223. Radium-223 is an isotope of radium that decays by emitting an alpha particle. And lo and behold, the radium went to the bones, it emitted its alpha particle, and it cured a lot of cancer. This was in clinical trials, and it was so successful, they had to stop the clinical trial because it was unethical to be giving anybody the placebo anymore. And so Xofigo is now a regularly used treatment for cancer that has metastasized into the bone. And so that works really well if you have this chemical similarity, right? So if it's here in the bone, you can use radium to mimic calcium and go there. But what if the tumor is somewhere else? Then we have to go back to the idea of how do we get the radioactivity to the tumor, okay? And that's where we start talking about radio-pharmaceuticals, okay? This is like, think of a Trojan horse, right? So the Trojan horse says, looks like an innocent little horse, but inside of it is an army, a lethal army. If you take your radioactive compound and you have a linker that goes to a targeting molecule that goes and finds cancer, okay? Could be a small molecule, could be a peptide, something that has a marker that will go find cancer cells. And you deliver this radioactive compound, when it gets there, it'll give off its nuclear payload. You'll have the main impact there on the tumor and less of an impact on the surrounding healthy tissue. So this is really valuable. It lets us have a better therapeutic dose with less of a side effect, okay? So the first agent that is FDA approved now to use this idea is Lutathera. Lutathera is based upon lutetium-177, okay, and they use it for prostate cancer, linked to a PSMA, which is a prostate-specific membrane antigen. But lutetium-177 decays by emitting a beta particle. A beta particle is just an electron. It's an electron that started out in the nucleus rather than the atomic orbitals, kind of like our gamma rays or like X-rays, except for their difference in origin. So it seems to work. It has some good efficacy. FDA approved. It is in use. But that beta particle will travel a lot further in tissue. So even though the PSMA brings it to the tumor and it starts its irradiation at the tumor, it tends to also go out into some of the surrounding healthy tissue. So what if we were able to, instead of using a beta emitter like lutetium-177, we were able to use something more powerful, something heavier, something bigger, something with a shorter half-life, something like a Mack truck compared to a bowling ball. So if we think of that beta particle as a bowling ball, and we think of this Mack truck being our alpha particle, that Mack truck's going to do a whole lot more damage. in a very short range than the bowling ball, right? We're not gonna knock down a few pins, we're gonna knock down the bowling alley, okay? So that's the idea of saying, can we combine this targeting with targeted radiotherapy with the Mach truck power of an alpha particle to get targeted alpha therapy? Okay, so to look at that difference between alphas and betas on a cellular level relative to a cancer cell, you can see that our beta particles will go through, generally they're making single-stranded breaks, and they have, a range of, could be up to 12 millimeters in tissue, and although it may start at the tumor, it can go outside of the tumor. Alpha particles, on the other hand, will keep their impact much more condensed and really cause a lot more damage right on the tumor. And you can see sort of the image here of this targeted alpha therapy with our targeting vector, our radionuclide, and really the damage staying mainly there on the tumor. So, what we need to do is find some isotopes other than radium, right? We know radium-223 works. Are there other isotopes that we can attach to targeting molecules to be able to deliver that radioactive power right to the tumor cell? And one that's possible is astatine-211, okay? So astatine-211 decays by emitting an alpha particle. There are actually two decay routes, but both decay routes emit one alpha particle. They also emit some gammas and some betas so that you can image it as well as treat with it, okay? And it gets down to something stable pretty quickly. So if you can get the astatine to the tumor, it can unload its alpha particle, its nuclear payload, then it becomes innocuous and stable, okay? So how do we make this? This sounds like a great thing, right? You put an alpha particle on a bismuth target and you get astatine-211. Sounds terrific. We just got to figure out how to get an energetic enough alpha particle to be able to do that. But before I do that, I want to point out one other thing. Again, bringing up a piece of the periodic table, you can see our astatine lies below fluorine, okay, as a halogen. So fluorine 18, if you remember I talked about fluorodeoxyglucose, so we could watch metabolic pathways happen because you're using it like glucose. Fluorine 18 is one of the main tags used for PET, or positron emission tomography. So if you have a targeting molecule that's going to go find cancer and let you image it, doing that diagnostic nuclear medicine based on fluorine 18, you might be able to do the same chemistry and attach an astatine in the place where you had attached the fluorine, and now you have what we call a theranostic. It's therapy and diagnostic pair, okay? Because you use the same targeting molecule. Now, somebody might say, astatine's a lot bigger than fluorine, and that's true. And that presents some issues in terms of the chemistry, and we need to understand the chemistry. The other thing to note about astatine here is it's pretty far down the periodic table. So yes, it's in the column with the other halogens, but it's right up against the metals. And you probably know that we call that a metalloid. So it may be that it acts like a halogen, and we can do halogenation reactions like we would with fluorine and attach it to a carbon. Or maybe it acts like a metal, and we need to chelate it, like we would bismuth or actinium or another metal. Or maybe astatine has some very diverse chemistry, and depending upon the oxidation state or the speciation, we can get it to behave either like a halogen or a metal. Sounds great. How do we learn more about astatine? There are no stable isotopes of astatine, so doing the chemistry on it, there is so little chemistry that is known. So that's one of the things we have to do, is understand the basic chemistry. And astatine-211 is the second longest lived isotope, and it only lives with a half-life of 7.2 hours, which means you got to do your chemistry pretty darn fast, okay? And you have to have some pretty sophisticated ways of knowing what's happening in your chemistry because you make so little of it, because we just can't order it from Eckert and Ziegler, right? I told you it's the second longest lived isotope of astatine. The longest lived is astatine-210. But astatine-210 decays to polonium-210, which is very, very toxic. So you really can't do the experiments with that either. So we have to learn all about the chemistry of astatine so that we can put it on a targeting molecule, so that we can bring this cancer-treating power to a tumor near you. Okay, so how do we make it? My little cartoon there showed an alpha particle running into a bismuth target. How do you get an alpha particle that's going fast enough to make that happen? You need an accelerator, okay? And so this is a cyclotron, and what happens here is you can inject in the ion source in the middle of the cyclotron, and you see there's like a little gap, and so the ion will get accelerated across the gap, and because it's now a charged particle in a magnetic field, it bends. And then it comes back to the gap, and it gets accelerated again, so it's going faster. So since it's going faster, it bends at a larger radius. And then it gets to the gap, and it accelerates, and then it bends. And it keeps going around in this spiral till you get to your extraction radius, at which point it could be 30% of the speed of light, okay? And then you can take it out and you can bombard it on a target. Fortunately for us, we have one of these cyclotrons here at Texas A&M. That's the instrument I referred to in the very beginning. We, in fact, have two of these cyclotrons here at Texas A&M and a number of other facilities. And so that's a whole nother talk about all the amazing discovery science that we do that the facility was built for. What we do for astatine is we take the K150 cyclotron there in green, which looks like that, and we use that to accelerate those alpha particles to what is 28.8 MeV per nucleon. Okay, so we accelerate our alpha particles, we extract them, we send them down the beam line to a target that looks like that at the end of that beam line, okay? That target is made of bismuth. So now, when we're done irradiating, sometimes the target looks like that, we basically have a whole bunch of bismuth, a whole bunch, maybe a gram, okay? And a very few astatines, okay? So we're talking about not just a needle in a haystack, but a needle in a Kyle field worth of stacks of hay. That's what we have to do, is be able to get that astatine out of the bismuth target so that we can get it on a targeting molecule and to a patient to take care of their tumor. So in order to do that, we have to dissolve, we take the target and we dissolve it in nitric acid, okay? Pretty strong nitric acid so that it all dissolves up. And you see in the first picture there, basically a little tube, sorry, that has our nitric acid, and in that solution is a lot of bismuth and a little bit of astatine, okay? So now we're gonna use some pretty neat chemistry called liquid-liquid extraction to get the astatine away from the bismuth, okay? So if I take what's in my vial there and I put it in the bottom of a tube, and it's nitric acid, so it's an aqueous solution, and then we put on top of it an organic phase, okay? Let's just say a ketone, okay? Because a ketone has lots of electron density around that carbonyl group. We happen to know that astatine likes that electron density if it's in the right oxidation state, and it will hang on to that organic, or the organic will hang on to the astatine. So if you do this, and you take your dissolved target with bismuth and astatine, and you put some organic on top of it, 1 octanone, let's say, shake it up so it becomes miscible. the astatine is going to hop onto the organic and say, I really like this organic molecule. I'm sticking with you, buddy. The bismuth doesn't care. It stays in the nitric acid. So then, after you mix it up, you let it separate. And now all of your astatine, or most of it, is in that organic layer, and the bismuth is still in that nitric acid layer. So now I just have to separate the layers, and I have gotten my needle out of my haystack, ready to head toward my patient. Okay? That's great. We can go one step better, because I don't know how much you guys have done with chromatography columns, where you have various different separation layers, right? And you can get many different stages of separation in one column. So that's what we did. We took a chromatography column. We took these polystyrene beads. You can think of them as, like if you have an English muffin and it has all those nice little nooks and crannies, and you put your butter on it, it just flows into those nooks and crannies, and it's all delicious. Well, I don't recommend eating this, but if you take your polystyrene that has all these little crevices in it, and you soak it in octanone, the organic stuff will get into those crevices, okay? And then you pack your column. And then if you take that column and you take your liquid, your dissolved target that has both the bismuth and the astatine in it, and you push it through the column, the astatine will hook onto the organic, which is tucked away in those nooks and crannies, and the bismuth will come straight through the column. Before we invented, the process by which people got the astatine out of the bismuth target took many hours and required like vaporizing the astatine and stuff. It really was not a good thing. We now can do this in under 20 minutes, okay? So this picture up here is our dissolution chamber. So at the very bottom, you can see a target, and there's the nitric acid dissolved, and you see some vapor there. But basically, you have your astatine and your bismuth. You run it through the column. The bismuth comes straight through the column, right? Because it's in the nitric acid. The astatine that's in there sticks to the column because it likes to hang on to the organic. And then you can flush with organic and get the astatine out in a very small volume, very pure astatine, in under 20 minutes. Amazing, actually. And then we went one step further and said, well, we're really good at making this astatine, and we're pretty good at studying some of the chemistry, because we do that too. But we have colleagues down at MD Anderson, and they're actually really good at that targeting molecule stuff. Like, how do they actually get it to the cancer, right? And so our proximity to MD Anderson is really valuable, because it means within a couple of hours, as long as they don't stop at Buc-ee's for lunch, we can get the astatine into the hands of radiochemists down there. So in order to do that, what we did is the step of taking the astatine back off the column, we paused and we said, let's just ship the dry column. And so we dissolve up the target, we run it through our column, the astatine sticks on the column, we throw the bismuth away. We take that column, we dry it out, we package it up, and we send it to MD Anderson. We send it to UT Health Houston. We send it to UT Southwest Dallas, where they're getting ready to go into a clinical trial with our astatine. We send it to our colleagues at the University of Alabama, Birmingham. We've sent some to Penn. We can ship it all over the country, actually. If you have to ship it overnight, then you have to depend on FedEx to get it there. If you can hire it, if you're within a few hours and you can drive it, it's really much safer. But we can deliver this astatine and get it into the hands of collaborators and colleagues around the country that can then work on developing some of those targeting molecules. So we're pretty excited about that. And this is the answer to Klaus. After 3 doses, you remember Klaus with all those dark spots all over his body? After 3 doses of PSMA with an alpha emitter, which in this case was not astatine, it was actinium-225, you can see that basically the cancer is gone. And if you actually look at the PSA numbers, which maybe your fathers know about, right, because they're older gentlemen, basically cured of cancer. Klaus went on to live for a number of years afterward. He had some side effects where he had trouble swallowing because the actinium had affected his salivatory glands. But he had a number of years of really good life after this treatment. And so this is really the power. I can remind you what Klaus looked like before the treatment. So this is Klaus pre-treatment, and then after 3 doses of targeted alpha therapy, basically cancer-free, and 1 more. So that's what we hope to be able to contribute to, is being able to save lives like Klaus. Along the way, we're doing some really neat chemistry, okay? And so we're looking at the bonds and how the astatine bonds to the organic molecules, the ketones. Can you then make it? Because I told you it was important what the oxidation state was. What was the speciation, right? Did it behave like a halogen? Was it behaving like a metal? And actually, we can control that by either reduction or oxidation into AT minus or AT plus. And we can control the strength of the bond by controlling the chemistry of what we interact it with. So we're doing lots of fun stuff along the way toward trying to help the world in terms of having another tool to treat cancer. So one might ask, well, where else can you do this, right? And the answer is not very many places. This is a map of the population density, and it shows you, well, here, I'll put circle. Well, there are 4 solid circles here. Those are the 3.5-hour radius of the 4 places in the country right now that make astatine-211, okay? Only the University of Washington and us actually deliver it outside of our own institutions, but Duke does some research and Penn does some research right there. Nusano, Ionetics, and UC Davis hope to someday be able to make astatine. But so the number of places that this can be done is very, very limited because it has a 7.5-hour half-life. So you have to be nearby the production to be able to do it. And the coupling of Texas A&M with the health institutions in this 3.5-hour radius between Austin, Houston, and Dallas is really remarkable and lets us do a lot of things. So I'm going to stop there, and I have to thank the team of people that work every day to try to help bring an end to cancer, or at least some relief to the people that are being impacted by it. And really the whole team at the Cyclotron Institute, because it is not just me or the students that I am fortunate to work with, but it really is a whole team that makes the cyclotron work, that makes this research possible. So I'm going to stop. I thank you for your attention. I hope the Aggies do well in their games tonight. Gig 'em.
Thanks, everybody. You'll see a notification later tonight.